Okay, so one of the major themes in the integration section on the BC exam are what we're going to refer to as Riemann sum problems. Okay, so what's going on here? Recall we have a curve. We call this f of x. We are trying to find the area under that curve between two x values a and b, and we know that the area of that is the integral from a to b of f of x dx. So in order to start developing technique for this, what we do is we look at how to estimate that area using known quantities. And we're going to use a specific example and 4 different ways of coming up with Riemann estimations and approximations. Each one's a little bit more complex than the earlier. Okay, so our specific example, we're actually going to use the sine curve, but we're going to raise it up by 2. Okay, so if I think about this, my sine curve is now going to bounce between 2, well, actually between 3 and 1, right? 1 and 3. And it's going to have its period from 0 to 2 pi. So what we're going to do is we're going to use our Riemann sums to estimate the integral from 0 to 2 pi of the sine of x plus 2 dx. Okay, and we're going to do this 4 different ways. So the first one we're going to do is called left-hand Riemann sum estimation, and we're going to use 4 partitions. Now, the more partitions that you use, the more accurate your estimation will be. We're going to see that 4 in this case works actually pretty well. And what we're going to do here is we're going to make partitions of equal size. There's nothing about Riemann sums that say they have to be of equal size, but usually it is helpful to kind of work from that point of view. All right, so let's take a look at what's going on here. If I look at my graph here, I actually have a bit of a mistake in the graph. Let's fix that. All right, let's make the graph a little bit more sharp here, because there's some stuff going wrong there. That's going to cause us problems later on, so let's fix that. All right, so there's my graph. I have to go from 1 to 3. Let's be more cautious here. Let's put that there, put that there, and put that there. There we go. That's a little more accurate of a graph from 0 to 2 pi, right? So this is at 1, 2, and 3. Okay, so if I build this into 4 partitions, I should have one at pi over 2, one at pi, one at 3 pi over 2, and one at 2. Now, if I'm doing a left-hand Riemann sum, I'm going to build rectangles based on the left side of functional value of each of these partitions. So the left side of this partition is here at 0. The functional value is there, and I'm going to build a cross, and I'm going to use this rectangle. Okay, so this partition here, the left side functional value is there, so I'm going to use that partition, that rectangle. Okay, so there's the left side there, that rectangle, and I'm again going to use the left side here and that rectangle. Now this looks like a horrible estimation for the area underneath that curve, but the argument is that it's going to be okay-ish, and if I actually make the partition smaller and more numerous, it's going to get closer and closer to the actual answer. But let's see how well we do here. If I go from 0 to 2 pi, right, the height of my first rectangle is 2, and its width is pi over 2. The height of the second rectangle is 3. Its width is also pi over 2. Height of this one is 2 times pi over 2. And the height of the last rectangle is 1. This should be f of x dx. There we go. Times pi over 2. All right, this allows me to factor out a pi over 2 and get 2 plus 3 plus 2 plus 1. That's pi over 2. Let's see, that's 2 and 3 is 5, and 2 is 7, and 1 is 8. So that's just going to work out to be 4 pi. So the argument here is that my estimate by left-hand estimation is 4 pi. Well, if we can do this by left-hand estimation, we can also do this by right-hand estimation. So let's draw our original graph again. 1, 2, 3, right? We're going to go to 2 pi. There we go. So we go up, down, and then back up, right? So this should be, we're going to do right-hand Riemann sum estimation, again with 4 partitions. All right, so we're going to go from 0 to 2 pi. This is pi over 2, pi, 3 pi over 2. And now instead of using the left-hand point of each interval, we're going to use the right-hand point. So if I go all the way up here to the right-hand point, cut over, I'm going to use that rectangle to estimate. To the right-hand point, cut over, I'm going to use that rectangle to estimate. The right-hand point to cut over, and the right-hand point and cut over. So we're going to say the integral from 0 to 2 pi is, well, let's see. The height of the first bar is 3 times pi over 2. Height of the second bar is 2 times pi over 2. Height of the third bar is 1 times pi over 2. Still be f of x dx here, right? So this is an approximation, plus 2 times pi over 2. So we can factor out the pi over 2. 3 plus 2 plus 1 plus 2, which again is pi over 2 times 8, which again gives me 4 pi. So now this does not always work. It's very not likely to happen, but because of the curve that we're constructing, it is working out that the left and the right hand estimation both happen to work out to 4 pi. Let me give you a hint. If that does work, chances are it's a pretty good estimation. But it's not always the case. So we're going to see 2 more versions of this. So let's look at another one. Okay, so when in doubt, make things more complex, okay? So we're going to use the same function, sine of x plus 2, and we're still going from 0 to 2 pi. And so let's get a drawing of our curve here. There we go up, we come down, and we go back up, right? So this is still going to be 4 partitions. So what we're going to do here is we're going to do a midpoint estimation using 4 equal size partitions. So this one's at pi over 2. This one should be here at pi. This should be 3 pi over 2 and then 2 pi. So what we're going to do is we're going to look at the midpoint of each interval. So the midpoint here is pi over 4. So pi over 4 is like there, and we're going to use that rectangle. This one is 3 pi over 4, right? So that's about there. We're going to use, actually, I know something here. It's there. We're going to use that rectangle. And then we use 5 pi over 4, which is here. So we use this rectangle. And 7 pi over 4 is here. So we use this rectangle. Okay, so it's a bit of a crowded graph, but we'll get the point across. So let's see what's happening here. So I'm taking the integral from 0 to 2 pi of f of x dx. And all right, this first rectangle is the same as sine of pi over 4 plus 2. Well, the sine of pi over 4 is just root 2 over 2. So this thing has a width of pi over 2 and a height of root 2 over 2 plus 2. Okay, so this one also is going to be a width of pi over 2, and its height is the sine of 3 pi over 4 plus 2 is still going to be root 2 over 2 plus 2. Let's see, this one also has a width of pi over 2. Its height is the sine of 5 pi over 4, which is negative root 2 over 2 plus 2. And finally, this last partition has a height of pi over 2. And let's see, this is going to be the sine of 7 pi over 4, which is negative root 2 over 2 plus 2. All right, so let's look at what happens here. We pull the pi over 2 out, and let's see, if I pull that pi over 2 out, I'm going to get 2 root 2's over 2 minus 2 root 2's over 2 plus 2, 4, 6, 8. And lo and behold, those cancel out, leaving with pi over 2 times 8, which is again 4 pi. So we took the functional values at the midpoints of each of the intervals as the heights, and then we took the consistent width of pi over 2, and once again, 3 out of 4 of our estimates came out as 4 pi. Might be a pretty good idea here. Slightly more computationally complex than doing the left or right hand, but still giving us the same answer. Okay, so I said there were 4 methods. The last one is more complex than the other 3. And it's deliberately designed to be more accurate, even though it is more complex. So we're going to go from 0 to 2 pi. This here is pi in the middle. We're going to make partitions at pi over 2 and 3 pi over 2. And we're going to call this the trapezoidal estimate using 4 partitions. Okay, so you can use more, but we're only going to use 4 for our example here. So what you literally do here is you take both endpoints of the interval and connect them, and that makes this a trapezoid. Same there. Same there. And same there. Okay, so let's think about this. This is the integral from 0 to 2 pi of f of x dx. So the first trapezoid has a base of 2 plus 3 over 2 and a height of pi over 2. The second one has a base of 3 plus 2 over 2 times pi over 2. This trapezoid has bases of 2 plus 1 over 2 times pi over 2. And this one has bases of 1 plus 2 over 2 times pi over 2. All right, so again, we're going to pull that pi over 2 out. So let's see, this is 5 halves plus 5 halves plus 3 halves plus 3 halves. Let's see, that's 10, 16 halves. 16 halves is 8, which gives me 4 pi. All right, so regardless with this particular function, regardless of which method we use, we keep getting this estimate of 4 pi. Now again, this doesn't work for every function. This function has some unique properties that make that happen. But if I were to guess what is the area underneath this curve, I'd probably think it might be 4 pi at this point. All right, so there is a way to do this using the fundamental theorem of calculus. I don't expect you to know this at this point, but I'm actually going to write it out so you can see that these estimates are actually accurate. Okay, so if I solve this problem, the integral from 0 to 2 pi of the sine of x plus 2 dx, by the fundamental theorem of calculus, it says that I have to take the antiderivative here. The antiderivative of sine is the negative cosine. The antiderivative of 2 is 2x. You can check for yourself that the derivative of this will be that. And I'm monitoring this on 0 to 2 pi. I take the negative cosine of 2 pi minus 2, or sorry, plus 2 times 2 pi minus the negative cosine of 0 plus 2 times 0. Let's see, the cosine of 2 pi is 1, so that's negative 1 plus 4 pi minus, and this is going to be negative 1 plus 0. Those cancel and tells me that the actual value here will be 4 pi. Now, this is something that we're not going to cover for a couple more classes yet, so just hang on to this thinking. But once we get the fundamental theorem of calculus in a later class, you'll be able to check against this and see that, in fact, the Riemann sums here are actually coming up with some very accurate estimations. Now, granted, getting an accurate estimation off of 4 partitions is fairly unusual, but it does happen to work well with this curve because of its symmetries. Alright, so we'll look at another example, and then we'll call it a day. Okay, so throughout this video, I've said that you do not have to have, equal sized partitions. So we're going to use this table to make an estimate of what would be the area under the curve from 1 to 12 of f of x dx. And we're going to use left hand. So we're going to do a left hand Riemann estimation to do this. Okay, so if I look at things, maybe I could draw a bit of a picture here. So here's my axes. There's 1, there is 3, 7, 8, and 12, right? So if I'm using the left hand estimations, I want to use the value 5 for 1. Okay, so this has a height of 5. At 3, I want to use the height of 6, right? At 7, I want to use the height of 8. And at 8, I'm going to use the height of 9. So if you're thinking about this, yeah, sure, 12 goes up to 10 here, but that's not going to figure into things because I'm using a left hand estimation. If I was using the right hand estimation, that would be in there. So these are the rectangles I'm going to use to come up with a left hand estimation for this Riemann sum. Now if I look, my first rectangle here has a width of 2, right? So that's 2, and its height is 5. My second rectangle, however, has a width of 3 to 7, that's 4, right? And it has a height of 6. Okay, so 7 to 8 has a width of 1, and that has a height of 8. And then 8 to 12 again has a width of 4, and that has a height of 9. So 2 times 5 is 10. 4 times 6 is 24. Right? 1 times 8 is 8. 4 times 9 is 36. So this is an approximation here, right? Let's see, that's 34 plus 8 is 42. 42 and 36 is going to give me 78 as my estimation there. Okay, so I have to be a little bit cautious about this because, you know, I'm not using equally spaced partitions, and that's okay. Riemann works even though the partitions are not evenly spaced. Sometimes you'll see problems on the BC exam that are not. You have to be cautious with that, but I can still get a Riemann estimation given the situation. So there you go. There's your video on Riemann sums.